Continuing in 3.2, let's look at some more concepts. Definition of a linear combination, which we've already seen before. The next few things will be very similar to what we have already talked about. Some I'll write down in detail and some I'll just kind of go over now that we're in our more general vector space concept. So linear combination, a vector v, so this is a vector v. So a vector v in a vector space, capital V, is a linear combination of these vectors in V. If you can write V like this, right? Just like before, where the C's are our scalar multiples. So that's what we know is familiar to us for a linear combination. So let's look at an example. I'm going to carry this example a couple times. We have 1x and x squared. Basically, this would be considered a subset of polynomials of n less than or equal to 2. And so is that, so we can talk about linear combination of those vectors. So let's just pick a vector, I don't know, x squared plus 4. Well, what we would have then is all linear combinations would look like this. Ax squared, a2x squared plus a1x plus a naught. So we can make this a linear combination of these by just choosing the correct constants. So this would be like your u1, u2, and u3. So each of those would be vectors in S. And we can, of course, make up x2 by choosing a2 to be 1 and a1 to be 0 and a naught would be 4. So we have indeed a linear combination. Okay, so that's how you can express it. So where are we going to next with that? We're going to spanning sets. So if this set is let's go back to this example. I wasn't done yet. So if this is my vector v, then v is equal to, let me do this a little better, is equal to, let's write it in that form using our u1 and u3. That would be, the linear combination would be, let's see, where is it? So it would be u3 plus, and then 0 u2, but we wouldn't put it, and then 4 u1. So that's how you would write v as a linear combination of those vectors. Okay, so that's exactly that form we're talking about. Okay. Just cleaning up my work a little bit so you can see it better. So that's kind of what we're getting at. So next, let's talk about spanning sets. This is definition 3.3. And this is, if I can write it, this is spanning sets. So this again will be very, very similar. Let's let S equal the set V1 to V sub K. And I do want to point out this could be infinite. So it may be infinite. So you could just say this form, comma, dot, 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 which means it would go on in that manner forever. So you could have an infinite subset. Okay, so that is a subset of capital V. V is a vector space. All right, so then the set S is called a spanning set. Not spamming, spanning. A spanning set of V if every vector in V can be written as a linear combination of vectors in S, which is what you would expect, right? So if every vector in V can be written as a linear combination of vectors in S. And we say S spans V. Okay, just like in chapter 2 or previous chapters we were looking at in Rn. Okay, so it mimics Rn exactly. So let's look at, actually we're carrying on that same example above. So let's consider polynomials of degree 2 or less. Okay, so that's as before, polynomials of degree 2 or less. So the question is, does my set above, does S equal to 1x x squared span P2? Or I've been putting it like this, P in less than or equal to 2. And of course it does. You can see that. I mean, you basically have every polynomial in P2 is defined to be like this. Like if you actually define that set, it would look like this. Ax squared plus bx plus c, where a, b, and c are anything. So a, b, and c are any real numbers. That's essentially how you define that set. And so that is exactly a linear combination of S, of the vectors in S. So of course, yes, it does work. So S is a spanning set. And you can literally put any coefficients in here and it would still span the set. It just wouldn't be like the standard set. Okay, so then let's look at, just one more case just to show another thing. So suppose W is 1x squared. Can you construct all vectors in P2? And basically you can't, right? I mean, if you have, so you have h of x is, it would be 1, well, not a 1, but all linear combinations will look like ax squared plus, say, c. There is no x in there. So you are not going to create or come up with that x. And what does that have to do with? What is like not being able to make that linear combination have to do with? It has to do with independence. Are these vectors independent of each other or linearly independent? Meaning, can you make a linear combination out of the other? And you can't, right? So these are linearly independent. That we'll define that in a second here, but that's what we're getting at. Which I guess is next. Okay, so next definition. This is definition 3.5. Is exactly that concept. Let's take a look at that. So let V be a vector space, and we'll say capital X is a subset of V. Then for V1 to V sub k in X, if R1 V1 plus R sub k V sub k equal to 0, and not all r's are 0, then V1 through Vk we say are linearly dependent, right? That's the same as before. So and not all r sub j's are 0, then we say the vectors v1 to vk are linearly dependent. So if the only way the sum is 0 is if all r's are 0, then the vectors are linearly independent. So I'd like to write that one down too. So if the only way the sum is 0 is if all r's are 0, then the vectors v1 to v sub k are linearly independent. Right? It's the opposite of dependent. So this one is the existence of not all r's being 0. This one, independence, means they all have to be 0 for that sum to be 0. And I need to, if you happen to have my notes, I will put sum there. It should be the vectors. I'm just going to say the vectors are linearly independent. Okay. So let's look at this example. This will do, well, we'll break this up this time. Okay, we'll do a couple examples next